I will introduce you. So yeah, Olga, thanks again for joining us here in the Qualcomm-UvA Deep Vision seminar. For everyone who doesn't know, which I hope there aren't too many, Olga is an assistant professor at the Department for Computer Science and also faculty at Center of Statistics and Machine Learning and Information Technology Policy at Princeton. Her research is mainly in computer vision, as well as machine learning, human-computer interaction, and fairness, accountability, and transparency, about which we'll hear a lot more today. She is also co-founder of the AI for All, a nonprofit to create diverse future generation of AI leaders, especially from historically excluded talent via education and mentorship. And back in the day, she has completed her PhD at Stanford and done a postdoc at Carnegie Mellon, and was, of course, vital in that dataset that we all know, ImageNet, and continues to work on it with work such as the ImageNet blurred version and her more recent research, which I'm sure we'll hear a bit more about. As for the questions or general information, again, we'll be recording the talk and putting it on our YouTube channel afterwards. And we will please collect your questions, and towards the end of the talk, 45 minutes of a talk, we'll have the questions in one collected Q&A session. And with that, without further ado, welcome, Olga, and yeah, stage is yours.
Oh, awesome, thank you so much. Everybody hear me, see the slides, all is good, right? Okay, excellent. So yeah, so I'll talk today about fairness and visual recognition, which is one of the research directions in my lab. And so we'll sort of go through both some of our work, and I'll sort of also try to put it in context of some of the related work as well that's been done in the space. That's the very active and growing research field. So first of all, to set the stage, so this conversation has been going on for quite some time around fairness, bias, inclusion within visual recognition, but sort of the latest wave of this conversation has really started as computer vision systems started actually being deployed in practical applications, and kind of these questions of sort of what are these systems really doing started to come to light more and more and more, both in the scientific community as well as in the public's eye. So starting around 2017, around 5 years ago, 6 years ago, there started being headlines like computer vision model that learns to increase attractiveness, quote unquote, by manipulating skin color, or machines taught by photos learn a sexist view of women, or facial recognition is accurate, but only if you're a white guy. And this is a very, there's some very deep questions about why this is happening. And this is, certainly not something that anybody intended to do on purpose, but yet this is very pervasive and problematic. And so there's some great books out there, and I'll refer you, for example, to a book by my colleague, Professor Ruha Benjamin, that's called Race After Technology, that sort of came out recently, that really does a very deep dive into some of the root causes and sort of societal structures that lead to these kinds of effects on a much deeper level. But for the purposes of this talk, and generally for the purposes of the work in my lab, right, so we do very technical sort of engineering work, and we basically simplify some of these things down to this cycle, right? So we're thinking about there's some human history of bias and prejudice, which we're not experts in, but we know that's there. And that's making its way into large-scale data in some way, and that's where we sort of our expertise starts to come in. The large-scale data informs sort of what is learned by the AI models. The AI models then make some decisions in the world, and then that becomes part of our history. And so the question that we ask is, can we adjust the AI design to try to mitigate some of these effects? And we put the emphasis on the word mitigate, right? Because we don't think this can be entirely eliminated. It can be eliminated in some particular cases, perhaps, but in general, this is just a very, very deep and complex problem. Even sort of what do we mean by the definition of bias? How do we, sort of our definitions of biases are continuously evolving. So sort of full elimination is not the goal, but the goal is mitigation. So throughout the talk, I'll sort of talk about three different pieces here, right? So the data and then the models and then sort of who is making some of these decisions. And we'll start by diving into the large scale data piece. So the big message here, right, is that just because the data is large scale does not mean that there's fair representation or unbiased representation. And one of the sort of best known works that kind of talk about this or demonstrate this is the work by Drs. Joy Blomwini and Tamid Gebru in 2018 called Gender Shades, where they talk about the fact that face recognition systems, so systems that look at a face and predict gender, and this is, by the way, a theme that will sort of come throughout the talk, is that when I talk about gender, I'm talking about a binarized, socially perceived annotation of gender expression, which is a vast oversimplification of the concept of gender, which is non-binary. But this is, this is sort of a common simplification that we do when talking about the technical fairness work. So in this paper, right, in Gender Shades, they looked at gender recognition accuracy on faces of men versus women and on faces with lighter skin versus darker skin. And they found dramatic disparities in error rates. So these systems were, within 1% error rate, less than 1% error rate on faces of lighter skinned males, and something like 16 or 17% error rates. This is commercially deployed systems, 16 to 17% error rates on faces of Black women or dark skinned women. And there's been, a number of work sort of identifying these kinds of effects, including one of our recent ICCV papers that I'm not going to get to talk about, called Understanding and Evaluating Racial Biases in Image Captions, where we study capture. So in Joy and Tamit's paper, so they pinpoint this problem to the lack of diversity, demographic diversity in face recognition data sets in particular. In our work, we look at the COCO data set and analyze demographic distributions within COCO, and again, kind of find similar patterns where dark-skinned females are dramatically underrepresented in this data set. And this can lead to some of the kinds of disparities in error rates downstream. But going deeper beyond sort of skin color or gender underrepresentation, there's also been questions about, for example, geographic diversity. So most computer vision data sets these days, including ImageNet, including Open Images, including many others, are collected via search engines. And by querying those search engines in particular ways, frequently using using English queries or translation into a few sort of common languages. And what ends up happening as a result of this data collection processes is that some countries become overrepresented. So primarily, these data sets come, for example, primarily from the US, and then entire continents like Africa are entirely underrepresented, entirely not represented essentially in these data sets. And this leads to all kinds of potentially problematic effects, like even for something as seemingly innocuous as object recognition, these models don't learn a representative view of common objects. So one example, this paper by the Facebook folks in 2019, they pointed out that something like soap, so the common household object soap, we all have it in our homes, these models learn US brands of liquid soap because they're trained on data from the US, and that's the most common version of soap in the US, and fail to recognize bar soap, even though that's the version of soap that's used in the vast, vast majority of the world. And again, all of these kinds of effects can be traced, at least in part, to image search. So, and this is, again, a large body of work that talks about kind of biases in image search, engines. So for example, if you query the search engine for a term like CEO, they'll give you this very Western male light-skinned version of what a CEO might look like, and not a sort of more diverse view. And there's been a large body of work also recently thinking about data collection practices more deeply from the perspective of who's included, from the perspective of consent, from the perspectives of privacy, from the perspective of ethics, and including some of the work mentioned on ImageNet that I'm actually not gonna dive too deeply in today, but I will point you to that, sort of analyzing this very popular data set and what can we what can we do better with it? It was sort of collected about 10 years ago. It has become extremely popular, but there's a variety of questions about what images are included in the data set, what concepts are included in the data set, the incidental people that are included in the data set, and sort of what can we do to try to mitigate some of these potential issues there. But the one piece of work that I do want to focus on today, looking at diversity in data sets, is work that's broadly applicable sort of beyond ImageNet to a variety of common computer vision data sets, so COCO, open images, some of the autonomous driving data sets, which is the work that we published in ECCV of 2020 called REVICE, for Revealing Visual Biases tool. And so our goal here was to develop a tool that takes as an input a visual data set and then reveals potential social biases. So our contributions here were to try to aid dataset creators and users by revealing biases in large-scale visual data that's sort of impossible to manually analyze, but where you might want to be aware of sort of what are the patterns that are hiding in this data. And so REVISE leverages the available annotations, the pre-trained models, as well as some census data in some cases to try to identify bias in the representation of objects. So for example, things like the soap issue, the representation of people of different demographics and of different geographic regions, and then suggests potential actionable insights to the user and sort of leaves it up to the user to decide if some of these patterns that are discovered through automatic means are actually problematic, or if they are sort of innocuous correlations like, you know, trees tend to co-occur with sky, and then like, yeah, that seems fine. And so let me give you just a few examples here, particularly thinking about sort of how people of different demographics are represented. And so again, I'll use sort of gender as the example. And again, I'm going to talk about context and images depicting males and females. And again, with the caveat of simplifying gender to binary, when in practice it is much more complex. So one of the analysis that sort of REVISE does automatically is correlating the presence of different genders in COCO with different objects and different scenes. So for gender here, we're using gender annotations derived from image captions. For objects, we're using ground truth object annotations grouped manually into super categories. For scenes, we're using a pre-trained places network. So sometimes, you know, we don't have access to these annotations, but we can take some of the off-the-shelf pre-trained models. Those may come with some biases. I mean, the manual annotations come with biases as well. That is, you know, that is definitely true. And the hope is that on average, despite some potential mistakes in all of these different types of annotations, we can try to identify some patterns that sort of may still be, you know, valuable to dig further into, sort of despite the individual imperfections. And so one of the examples that we've identified here, right, for object categories, so for example, sports objects in COCO tend to be more correlated with males rather than females in images. Or kitchen objects in COCO tend to be more correlated with females than males. This is sort of consistent with some of the prior work as well as some of our expectations. And similarly for scene categories, we might notice that outdoor sports fields and parks are more correlated with males, and shopping and dining scenes tend to be correlated more with females. And so, you know, the actionable insight in the tool kind of tries to give you some actionable insights depending on the different types of analysis, is that in this case, the user may want to collect images of the underrepresented gender with the corresponding objects or scene if the user sort of deems this problematic given the goals of their data set. So let me give you another, so this is sort of just a kind of correlation in terms of presence or absence of these objects or scene. Let me give you sort of a more complex example. So going a little bit deeper, we're looking at the interaction between objects and people of different gender, but we don't have interaction annotations here. And so we're going to use the person-object distance as a proxy for interaction. And so, for example, this is a musical instrument called organ. This correlates sort of with both the presence of males and females in the data set. But when we look at actually the bounding boxes of these objects, when we look at their distance, it turns out to be that females tend to be much further away from this, from organs than males, which potentially suggests that in this data, the males are more frequently depicted actually playing the organ, and the females are just kind of correlated with this object, but not necessarily interacting with it in the same way. And again, the actionable insight would be to consider equalizing the level of interaction with the object if that is warranted, or leave it as is if this is consistent with your intention. And finally, sort of the last the last kind of level of depth is we can actually directly analyze the differences in portrayal of different genders. And so here for each object class, we can learn visual classifiers for recognizing these objects when it is present with females versus when it is present with males, and identify classes with the most stark differences between genders. And so some of the objects that pop out within COCO, within open images, are sports uniforms. This is consistent with some of the conversations that are going on in the sports community now around uniforms that female athletes are expected to wear as opposed to uniforms that male athletes are expected to wear, as well as a concept like flowers, which you wouldn't necessarily expect to have any kind of differences in co-occurrence, but it turns out that flowers occurring with females tend to be more of these kind of stock stereotype photographs, and with males it tends to be more in like conference room scenes during a business meeting, for example. And that is something that we were not aware of in these data sets, and that seems like something that data set creators should potentially consider and address. And again, the actionable insight would be to collect more images of each gender with a particular object in perhaps more diverse situations. So I will sort of move on to, from the data, I'll kind of summarize some of the key takeaways here, which is basically that we need targeted interventions to both increase representation, to examine and understand the data, and to try to constructively engage with the raised ethical issues. And again, I didn't spend very much time on some of the work that sort of connects some of the more technical finding to the more ethical concerns. But again, there is a very large body of literature that starts to think about, data collection practices and how we go about that, and how do we sort of change our procedures for ensuring privacy, ensuring consent, ensuring sort of informed participation, paying our crowd workers fairly, and things like that. But I wanted to give you an example of basically a core technical piece of work that really leverages our core technical expertise to try to address some of these issues, by providing a very practical, usable tool to the community that's sort of generalizable across data sets, and tries to solve some of these problems in a way that hopefully is helpful to many of you here who may be working on computer vision models or data set collection. And so I would ordinarily sort of pause here for questions, but let me keep going, and we'll leave time at the end to ask questions both on the data piece and on all of the other pieces as well. So one of the challenges, of course, with thinking about fair and representative data collection is that data will reflect our world. And our world is not fair. Our world is problematic. And the sports uniforms example is one version of this, right? This pattern that's revealed in the data is actually consistent with some of the problems that exist in the world today. So one of the questions we're always asking is sort of, should the data be representing the world as we hope it to be, or should it be representing the world as it is now? And kind of how do we, what is a good target or unbiased distribution with respect to what, and things like that. And so while there is certainly a lot of work that needs to be done on the data side, there is also a lot of opportunities to think about how do some of these potentially problematic patterns in the data, how do they affect the downstream models? How do they become integrated? How do they become learned in the model? And what are some of the algorithmic interventions where, even though the data reflects perhaps our world as it is now, or perhaps is even a biased view of the world as it is now, how can we think about, from a modeling perspective, intervening and training models that are more representative of, for example, the world as we wish it would be? And so there's many, many different challenges in building fair models, and many different research questions that arise out of this. And one of the sort of, I do want to connect this to some of the very classic computer vision and machine learning work on learning with long tail distributions, right? You have more example of some categories or some subclasses than others. This is a very classic problem that's a long-standing problem within computer vision and machine learning that's been worked on long before some of these more practical fairness conversations have started coming to light. Similarly, there's a lot of work on interpreting the model, right? So if you can understand what exactly the model is doing, that can help you identify what are some of the biases that may have been learned in the model and potentially move towards trying to correct some of these. And I will, give a plug here again for a paper that I'm not gonna be able to dive into, but this is a recent work called Hive on evaluating interpretability methods using human studies. Just came out on arXiv about a month ago, designing a new framework for how to quantify a range of human interpretability methods, sort of quantify with some metrics using crowd workers to kind of figure out to be able to more fairly compare different interpretability methods. There's, of course, similarly to interpretability, there's efforts to try to analyze whether the model is sort of right for the right reasons, even when it's making predictions, sort of what is it basing its predictions on, and try to identify if the predictions, for example, for action recognition like tennis is based on the fact that there is a tennis racket, or it is based on, for example, the gender of the person in the image and so on. So a lot of kind of interpretability work specifically applied to the fairness question. There's work understanding bias propagation, and again, I'll point to the same paper that I already mentioned in the previous work on understanding racial bias in image captions. So I've mentioned this is the work where we annotated demographics on Coco, but what we actually did with them is we studied how bias from manual captions propagate. So what kind of bias exists in the manual captions on Coco and how that propagates into the automatic captions that are being generated. And then, of course, there's questions about quantifying fairness, right? So all of this is sort of very complex, and questions about like, what is the right fairness metric? How do we measure the fairness of a model? And again, lots of work in this space. We'll quickly flag our ICML. I'm sorry, it should be ICML. It's not ICLR. It's ICML 2021 called directional bias amplification, where it proposed a new metric for measuring how much bias from data is amplified by the models. And finally, again, lots of work, including, for example, the Fairness in ML textbook being written by one of my colleagues at Princeton, Arvind and Ryan, and along with Solon Barokas and Moritz Hart, who are leaders in the fairness space, that actually provides a textbook about some of these concepts. But again, let me dive into one particular sort of line of work that we did in this space. Again, sort of very technical line of work, where our goal is to teach a classifier, a computer vision visual recognition classifier, to ignore a known spurious correlation in the data. So we assume that we have a training distribution, which is a skewed distribution. So for example, the target label is correlated with a protected attribute like gender or race. So one of the kind of challenges with talking about this work, in particular about, so some of our answers is gonna involve doing a GAN that's gonna automatically generate these images. One of the challenges is that it's actually quite problematic to show generated images depicting different gender expressions, sort of automatically manipulating gender expression in images and sort of showing some of those results. So I'm going to use a much more innocuous example here. So so all of the quantitative results I show will be with gender as the protected attribute. But for the purposes of sort of explaining the method and explaining the work, I'll use a much more innocuous example, which is that suppose I'm trying to train a classifier that is trying to predict whether the person in the image is wearing a hat or not. And suppose that this target label of hat or not hat is correlated with a protected attribute, And in this case, I'm going to use the presence of glasses as a protected attribute. It's not really a protected attribute, right? This is just a proxy for something like skin color or gender. I just want to steer away from that for the sort of technical discussion here. So as you can see in these images, so the top row contains, this is our training data set. The top row contains images of people with hats. The bottom row contains images of people without hats. And you might notice that the top row contains 4 out of the 5 people are also wearing glasses. And in the bottom row, only 1 of the 5 people are wearing glasses. So what is the problem with this? Well, potentially nothing, except if the classifier actually learns to recognize hats by specifically looking at the glasses. So learns to recognize sort of the hat and the glasses together rather than really focusing on our target label of hat. And the way we're going to test whether the classifier has learned this correlation or not is by testing this on images that are more balanced, right? So we're going to test it on images with hats and images of people without hats, but we're going to decorrelate it with glasses. So we're going to do an equal balancing in the training data. And so this is quite a well-defined problem. So this is sort of taking all of the much of the complexity and the fairness conversation out of it and sort of grounding it into a very concrete technical problem. And so our first work in this space with this problem setting was published in CVPR of 2020 called Towards Fairness in Visual Recognition. And we're basically sort of taking this problem, we're proposing a simple data set with controlled biases. So we manipulated CFAR to introduce some of these kinds of correlations. We manipulated some smaller versions of ImageNet to introduce these kinds of correlations. And we analyzed multiple bias mitigation techniques. So we sort of ran wide, so there's many complex tables with all kinds of different results in the paper to try to identify what kind of techniques may be well suited to tackling this problem. And then we validate on more realistic benchmarks, specifically the Celeb-A data set. So some of the key observations here were that oversampling and reweighting, this is well known in the community, but sort of verified, the oversampling or reweighting this training distribution is prone to both overfitting as well as numerical instability during optimization, particularly in settings where you have a high degree of skew and high degree of correlation between the target label and the protected attribute. A lot of the literature suggests adversarial debiasing for this kind of problem, where you're basically training a classifier with a representation that is invariant to the presence of glasses. So it turns out, at least in our experiments in a variety of settings, adversarial debiasing significantly impacts accuracy. So it does a reasonable job of debiasing, but it significantly drops the accuracy of the target classifier. We sort of dive into some of the reasons for that. But the method that we found that works sort of really well and the best on this, again, across a variety of settings, is doing domain independent training. So meaning that we train basically separate target label classifiers for each value of the protected attribute. Now, this is certainly not very scalable if you have, multiple protected attributes with multiple groups within each attribute. But for something like gender, when it's simplified to binary, you train a separate classifier for men, you train a separate classifier for women, and that tends to work quite well at learning a debiased recognition model. But this was sort of one answer, and this is a reasonable sort of first answer. But then we asked kind of a more complex question, which is, can we actually try to generate some of the training data that we need, right? So sort of straight up reweighting or straight up resampling that runs into issues, but can we do a more targeted data generation where we sort of rebalance the data and generate some of the examples that we need, but do this automatically in a way that's not just sort of replicating the training samples. And so what we're trying to do is basically for every training image, we're trying to generate a corresponding training image that kind of has the opposite protected attribute, right? So if you have images of people wearing hats and glasses, we're trying to generate an image that is wearing a hat, but not glasses. And if we have an image of a person without a hat and without glasses, we may want to add glasses. And so again, in practice in sort of more real world settings, what we're doing is trying to manipulate gender expression to, again, rebalance on that dimension. And so how do we do that? So we do that using GANs, in particular progressive GANs here, but we've actually tried with a range of different types of GANs. And so what we do is we take a GAN that's trained on real world data. So for some hidden variable Z, for everyone, we can generate a corresponding image X. We can train a glasses classifier, so classifier for our protected attribute or gender classifier on this, on real world data. Again, using, so it is going to be a biased classifier, that is correct. So we'll get to that in a second, but we can train classifier on real world data that takes an image into range of 0 to 1 for the label. This allows us to classify both real world data as well as any data generated from the GAN, and then kind of project it back into the latent space of the GAN and classify each latent space, also sort of provide a label, each point in the latent space, provide a label for whether it's more likely to generate an image that has, of a person that has glasses or a person that does not have glasses. And correspondingly, then that allows us to train a glasses classifier in the latent space. So this is a well-known sort of strategy. In particular, Emily Denton and others have shown in 2019 that this can be done very effectively, and in particular that this can be done using linear classifiers for some of these protected attributes. And so this makes our job a lot simpler in that we're actually just training linear hyperplanes in the latent space. So what is the problem with this? So the problem is, as you might imagine, is the fact that the classifiers are themselves biased. And so given a particular point in the latent space, right? So suppose this is a negative point, so this is going to correspond to somebody without glasses, can generate the corresponding image, and we can say, okay, so suppose we're sort of moving perpendicular to this glasses hyperplane, and we're trying to generate images that are sort of similar to this image, but with the addition of glasses, or images that are similar to this image, but moving in the direction of a different gender expression. So what ends up happening is that you can generate these images, but of course, because the classifier, because the data originally had correlated the presence of hat with the presence of glasses, as you move in the latent space, sure, you're going to be adding more glasses, but also you're going to be adding the hat, the target label that you do not want to add. And so what do we do with that? Well, so we try to explicitly debias it. So we try to explicitly counteract this. And the way we do that is we can also train a target label hyperplane, for example, for our target label of has had, using exactly the same technique. We train it on real world data, we apply it to GAN generated images, and we sort of back project it into the GAN latent space to obtain, again, a target label linear hyperplane. So now, inspired by some of the work from 2018 by Brian Zhang, as well as Margaret Mitchell and other folks, we can now move in this latent space, still moving across the protected attribute hyperplane, so still sort of changing the gender expression or changing the presence of glasses in these images, but we're now moving parallel to our target hyperplane. So that means that if the original image had a hat, we would like it to still have a hat, still have the same hat score, but just try to change the score corresponding to whether the image has glasses or not. So when we do this, the updated images look much more reasonable. So the original image did not have glasses and did not have a hat, and the final image does not have glasses, does not have a hat still, but does have glasses. You may notice, though, that a lot of other things about the image, in fact, have changed, and that is true. So that is one of the, so I'll talk in a second about sort of the pros and cons of this approach. And this is certainly a very valid criticism, right? So we're basically controlling for our target label, and we're changing the protected label. But yes, along the way, I mean, this is a very complex space, and lots of things will change. This is not quite, this is real world data. So this is not going to be quite as simple as just like, take this image, and just add glasses onto it. Before I sort of dive into the pros and cons, right, let me just kind of finish the method, right? So basically, we are going to take we're going to generate some images from this GAN space. For every image, we're going to take this image and we're going to generate a paired image to it. And this is this paired image. So from this image Z, we're going to generate a paired image from point Z prime. And this is going to be an image that has the same target label score, so the same amount of wearing a hat, but the opposite protected attribute score. So if the score for wearing glasses was 0.7, likely to be wearing glasses, now we're going to have a score of -0.7 for wearing glasses. And because all of these hyperplanes are linear, this is actually very straightforward. Right? There was actually a closed form solution for how to do this. If you're going to do this with multiple protected attributes, then things become a little bit more complicated, but still very, very attractive. Okay, so let's talk about the pros and cons of this. So one of the big pros is that we can do this using a single GAN for multiple targeted protected labels. And this was a lot of the prior work. I'll show you some comparisons in a second. A lot of the prior work actually did this using conditional GANs or using multiple GANs for different protected attribute and different target labels. We can do this with a single GAN. This method preserves interclass variation. So because we first sort of sample uniformly from this GAN and then do this paired augmentation, whatever interclass variation existed, that is still preserved. We're just sort of generating a paired example for every original image sample from this distribution. This, by construction, ensures independence between protected attribute and target label in the generated data. Again, just the algorithm is specifically designed to do that. And finally, it can be generalized to multiple protected attributes, basically by learning multiple hyperplanes and controlling for all of those during the generation process. What are the cons? So first of all, the classifiers need to be at least reasonable, right? So if you can't train a reasonable classifier in the real world data, this is going to fail. This might add other correlations unless you're explicitly controlling for those. And of course, GANs are tricky. So it actually took us a really long time to get this to work in practice just because GANs are complicated. So let's talk about evaluation here. So we're going to evaluate these classifiers trained with our generated data. And so the setup is going to be the celeb-A data set. The protected attribute is gender. And then there's 26 different target labels. And for example, hat is one of the target labels. We're going to do this along 3 fairness metrics. So one is the difference in equality of opportunity. So this is the absolute difference between the false negative rates of each target label across genders. And so there's sort of the original version by Moritz Hart and others in Europe, so 2016, and then there's sort of an adapted, extended version of this, sort of adapted to the sort of continuous output setting that we use in practice. The second is we're going to evaluate bias amplification. So this is how much more a target label is predicted with each gender compared to what was expected from the training distribution. Here we use our again, ICML 2021 work on directional bias amplification. And finally, we're going to evaluate directly the KL divergence between the histograms of target label score distributions across genders. So both the difference in equality of opportunity and the bias amplification scores, so they rely on a particular hard threshold for making classifications that has to be tuned. The KL divergence does not. So that's sort of the advantage there. All right. So 4 different results. The first is comparison to a baseline model. So a baseline model is basically just something that trains these classifiers on the celeb-A data with 0 intervention. And so sort of as expected, right? So this is sort of a sanity check, right? Our model does better across the board on all the fairness metrics, and lower is better on these metrics. We compare this against the weighted model and the adversarial debiasing model. So there are pros and cons versus the weighted model. So the pros and cons are basically that we do, so we do better in preserving accuracy, so in preserving AP, which is not, a fairness metric is just sort of how well does this classifier perform. The con is that, basically the weighted model very, very explicitly and very strongly debiases. We have sort of comparatively less amount of impact on the debiasing, but the weighted model actually almost sort of pushes it to the other extreme, where it learns sort of almost a negative correlation between these attributes. But then we do better than the adversarial debiasing methods sort of across the board, both a little bit better in preserving accuracy, but also better in the fairness metrics. So as I mentioned in the previous paper, right, one of the methods we discovered that had worked really well was domain independent training, where you basically train a separate model for classifying cats on people who are male versus people who are female. So we compare against the domain independent version. So we do better when the skew, so the correlation between the target and protected attribute is low, but we still do somewhat worse when the skew is high. So the domain independent training still works the best when there's a very high degree of correlation. And finally, we compare against a variety of other methods like fairness scan, for example, and sort of demonstrate that we are better across the board. And so, publish in CVPR. All right. So this brings me sort of to the end of the kind of technical portion of the talk, right? So we've talked about the large scale data, and then we've talked a little bit about the AI models, right? So we need to understand, quantify, and mitigate bias propagation by innovating on the technical front. And there's a lot of technical work that kind of can be done in this space, both on the sort of theoretical guarantees front, but also on the more practical sort of engineering, how do you actually build some of these systems. But I will point out, and I will very much highlight this, that there's also very much a need, particularly as we get deeper into this study, to engage with a broader interdisciplinary team of researchers. And so, for example, some of our more recent works, we're starting to grapple with more of the kind of complex questions about intersectionality in these settings, and sort of what does it mean to have multiple protected attributes, and how do you really deal with extreme imbalance when you're considering all the different possible gender expressions, and then it's becomes a continuous variable rather than a binary discrete variable. And more as you sort of go deeper into this work, I would very much encourage you all to at least read some of the more interdisciplinary work that kind of points out some of the kind of interesting problems that arise in this setting. And so in the last 5 minutes here, let me talk about the last piece of this cycle, which is the question about AI decision makers, right? So any kind of discussion about fairness or bias mitigation in these systems is really not complete without talking about who is actually making these decisions, and who is actually building these systems, and who's actually deploying them, and who's actually designing metrics for quantifying bias, for example, for evaluating these systems. And this, I hope, comes as no surprise to you, right, that we have a diversity crisis in this field. So there has been a range of statistics and articles written about this and sort of pointing out some of these issues. So, for example, the AI index report that came out of the Stanford's Human-Centered AI Institute in 2021 demonstrates that within AI, we're about 16% female with some of their metrics. We have less than 1% of folks who are Black or are African. We have less than 1% of folks who are Hispanic, Latino, or Spanish origin. And then there is a lot of kind of great work written about both these statistics and then the impact that they're having on people, both the impact that this is having on the technology, where some of the people who are affected by the technology are not represented among the decision makers, as well as sort of reasons for why we have this diversity crisis. Why are people not joining this field? Sort of what are some of the structural issues that are driving them out of it? And as an answer to some of these concerns, so about 5 years ago, we co-founded AI for All together with my then PhD advisor, Professor Fei-Fei Li, who hopefully many of you know about, as well as Dr. Rick Sommer, who's an expert in K-12 education. So AI for All is a nonprofit dedicated to increasing diversity and inclusion in AI. And so we sort of saw this as a very critical problem to try to address. And we believe that the solution starts with education, and in particular starts with education quite early on. So we're celebrating at AI for All, celebrating our 5th birthday on March 8th of 2022 on International Women's Day. And our goal is to educate and support a diverse next generation of AI leaders. So we're very focused on sort of identifying students who are going to be likely leaders in whatever field that they choose to be leaders in, and trying to show a path for them within AI, trying to sort of get them excited about this field, give them some of the technical tools they need to succeed in the field, and trying to create a community for them to stick together and to kind of continue their AI education as a team, as a cohort, and hopefully have that serve as a sort of shield of protection, for lack of a better word, against some of the cultural issues that exist in the field right now. And so to do that, we've partnered with 16 universities so far to run summer programs for high school students from historically underrepresented groups. We've launched a free online open learning platform and partnered with high school teachers in some of the districts that serve students who are historically underrepresented, in particular, some of the low-income districts. We've created recently college pathways. So we launched this during the pandemic in March of 2020. That was a challenging time to launch something, but it's actually thriving sort of somewhat surprisingly despite the timing. College pathways, so this is for students, again, from underrepresented groups who are already in college. And then we're providing lifelong training and mentorship and leadership opportunities and community events for our alumni who attended these programs. And my all-time favorite quote, and part of why we do what we do, is a student who attended Stanford AI for All in 2016, who said that until this program, I never thought that people who look like me could succeed in computer science and AI. So I will pause here. So we've talked about ways in which we can adjust the AI design to try to mitigate some of these bias effects. So we've talked about the large scale data piece a little bit, talked about the AI models. We've talked about some potentially constructive solutions on trying to educate a diverse next generation of AI leaders. Give a huge shout out to many of my students who have been involved in this work, particular Fei Wang, who's about to graduate and is looking for opportunities both in research and in academia and industry, Kai-Yu Yang, who is on the faculty job market, and then Nicole Meister, who's applying for PhD programs this cycle. Thanks very much. Happy to take questions.
Great applause from me for all of the participants. Thank you for the great talk. Yeah, let's start with the questions. Feel free to post them in the chat, or just post a +1 or something, and then you can also ask it yourself. We already have one question here, which is, how do you see, and thank you for the session and excellent insights, Olga. How do you see the approach of data-centric AI as proposed by Andrew, and much smaller and more focused data sets, and somehow a different way of training algorithms having an impact to solve the bias problem in AI? Especially, I guess, would having smaller data sets help to have better balanced data collections, where having big data sets does not really matter anymore?
I think we need all the help we can get to solve these issues. I think that I like that this is sort of a new framing of the question. That the one that I'm more commonly asked is sort of like, should we do data work or models work or sort of theoretical work in this space? And the answer is all of the above. Like, yes, please. I think there is not going to be a single solution. There's not going to be a simple solution to this. And I think sort of the more diverse tools we have at our disposal, I talk about sort of demographic diversity and representation, but the reality is sort of part of why actually demographic diversity matters is that leads to diversity of thought and creative ideas and creative approaches. And so actually, I think we need sort of as much diversity in our toolkit to try to engage with these issues as possible. So yeah, I mean, that's the long and the short answer to that.
Right, thanks. Kes, you have a question?
Yes, thank you, Olga, for a great talk and taking the effort to deliver the talk in the midst of CVPR rebuttals. Much appreciated. So yeah, there is bias in data, big problem. You use data to also mitigate a bias in your models. Now, there is also work in the fairness literature that has shown that there are algorithms models that amplify bias.
Yes,
right, and
most of them
potentially even more worrisome than the bias in the data sets themselves. right? So are you aware of work that can sort of like quantify or qualify whether a model amplifies bias, to what extent, and how to fix it once the model already exists?
Yes, so work that can quantify bias, yes. So Angelina Wang and Olga Russakovsky, ICML21 directional bias amplification. Correct, yes. So exactly that question is, how do you quantify bias amplification between data and model? Works that try to mitigate it, right, so once the model already exists, so that's sort of the tricky part, because I think a lot of the algorithmic fairness work actually, exactly tries to mitigate the issue. So there are certainly things that you can do once a model exists. And so in the CVPR 2020 paper, so they use as CVPR 2020 works here, so towards fairness and visual recognition, effective strategies for bias mitigation. So one of the solutions is actually a post hoc reweighting of, so you basically have a softmax at the end, you are reweighting it according to the target frequencies versus actual frequencies in the data. And that's actually sort of surprisingly effective at trying to mitigate the bias. So you can do things that are sort of post hoc interventions during inference time that don't require retraining the model. But it's challenging, of course, that sort of assumes that you have a softmax classifier, you have access to these weights and so on.
Okay, thank you.
Great. Next question, Nanette.
Hi, thanks for the talk. So this is a hard problem to solve, obviously, but I worry sometimes if we don't even have the right paradigm to try and start solving this problem, because we rely a lot on labeled training sets, even to debias. And then even if we don't use labeled data sets, then we have a labeled test set that we evaluate on, but also kind of optimize on, because we make model changes based on the results that we get. So even for the things that we don't have labels for, and of course, even labeling has a scaling problem, especially with these protected attributes. So do you see any new sort of paradigms emerging that you feel are promising in this direction? Or are we doing the same thing of trying to optimize metrics until we hopefully solve it at some point?
So absolutely. So first of all, I think it's called UDIS, I think is the abbreviation, but the work out of from Judy Hoffman's group at Georgia Tech. It's a recent paper that talks about unsupervised bias discovery and mitigation. So absolutely, yes. Part of the challenges, right, with unsupervised discovery, of course, is that what's going to happen is you discover patterns that are not necessarily correlated with sort of societal protected attributes. So you discover patterns potentially that are that sort of don't have quite the same societal impact or societal concerns associated with them. But absolutely, there's sort of more and more work of kind of either doing this unsupervised or with very few labels and things like that. I think as with a lot of computer vision and machine learning, we're sort of moving in that direction. I think in terms of optimizing metrics, so I think one of the things that I really like about this field, so we do, I mean, like my lab does a lot of work in sort of more core computer vision as well. But what I really like here is that almost inevitably, basically all of the work is a tight coupling between like data analysis and metrics and data and models. And like in this space, you really are sort of, I would say all of the researchers are really thinking about the full pipeline, and that's kind of very refreshing, I think, in many ways, because in fact, sort of like even if you're kind of focusing on the model, you're thinking about the metrics very deeply, and then usually, so this is like if you look at sort of the history of like our work, but I think this is true for many labs, you kind of publish a paper on the model, and then in doing that, you like really identify some flaws with the metric. So then you kind of publish a paper on trying to fix up the metric, and then you kind of realize that really the root causes the data. And so then you kind of do your next work, like really diving into the data. And that's, I think that's really great and an excellent way of sort of thinking about it. And I think machine learning, computer vision fields in general could serve to do more of that. So basically the question about like overfitting to metrics, I think the metrics are evolving very rapidly as well, much more rapidly than in some of the more established fields.
Okay, great. Thank you.
Cool. I also have a question. It's more of a fluffy one, I guess. I'm seeing lots of works that, well, we're kind of in computer vision moving more towards the NLP direction of just using sheer scale to solve lots of problems. And these models end up being a lot more robust and have astounding zero-shot capabilities. But of course, now we can't even analyze the training data sets anymore. So I wonder how you're viewing this trend, and like also how you see the role of academics in this new trend.
Yeah, that's I had an answer, but then I think the role of academics is that part kind of threw me. So I think in general, my general take on all of this is I think it's very hard to like fight against trends like this because they are fueled by, like, at their core, the desire to make these models work better, right? And in particular, you know, computer vision, I mean, we can take a sort of more cynical view on this, but the reality is, like, there are so many applications in the real world that would benefit from better computer vision, right? Like, you know, I mean, autonomous driving is sort of the common one that people will talk about, but like autonomous driving, right? This is not just for fun, right? This is hundreds of people dying every day in car accidents, which could be solved. This is, you know, accessibility for people who are not able to drive themselves and like are basically constrained in terms of where they live and what they can do. That would be alleviated, right? This is environmental impacts. Like there's just you know, application of computer vision in medicine, right? Application of computer vision in agriculture and like food distribution and deforestation analysis. Like there's just so much that can be done with this that I have a really hard time making any kind of argument about, like, oh, you know, we shouldn't be basically running as fast as we can towards this goal, because I think there's just so much that can be done with this, like if we kind of figure out how to do this. And so from a you know, from a fairness perspective, I think the goal of the fairness field is to kind of keep up with that. Yeah, like the data sets are getting bigger, so if we need, you know, more and more tools like REVICE that can, you know, how do we analyze this? How do we do this with fewer labels? How do we try to kind of keep up with these trends, but provide sort of constructive solution? Because nobody wants to build these systems in a way that's biased. Like that's not the intention. People are just trying to do this faster so that we can have this impact, like so that we can do good in the world. I don't know. Maybe I'm like too optimistic about this field, but like I like to think of this as in a positive light. And so I think to your question about the role of academia, so I think there is tons of what we can do in academia to try to help with this. And for example, right, so you know, all of this work is done in academia. There's a lot of academics who are engaging with some of these questions and are able to provide meaningful and constructive solutions and meaningful and constructive sort of methods and frameworks and ways of thinking that influence both the academic and the industry research and I guess deployment of these systems as well. And I'll say that there's, you know, particular advantages within academia, right? So things like interdisciplinary work. So being at institutions that have scholars across a wide range of fields where some of this work that really moves kind of outside of the core technical space, but towards much more interdisciplinary analysis, like that is a great thing to be doing in academia and to sort of actually leverage kind of the full potential of academia. We work with, you know, academia, you get access to a lot of students. Like a lot of this work is being done by young people who are coming into this field with bright new ideas and new ways of thinking and sort of their insights. And that's, you know, quite quite a unique opportunity to sort of like really think creatively about these ideas. And finally, you know, in academia, you're not constrained by immediate impact. And I know that there's some industry research labs that are, you know, really thinking about broader long-term impact, but it is really unparalleled in academia. And, you know, certainly if you compare kind of academia to the average industry lab, like we're just able to think on a much broader time horizon in terms of what will be the trends over the next, you know, 10, 20, 30, 50, 100 years, and kind of how do we set up the field for success on those kinds of time horizons.
Cool, thanks. Yeah, that's a nice note to end things as well, thinking about the next 100 years.
The next 100 years,
Yes.
that's right. We'll have perfect and unbiased systems in 100 years.
Yes. But yeah, I also share the notion of, I think we can be pretty optimistic. Like there's new challenges, which is exciting. Like how do you find the biases of models where you can't access the training data, let's say. But yeah, we're already going a bit over time, and there's no question here left so far. So again, I would like to thank you, and I'm gonna stop the recording now.